So need not be but one thing is for sure, that all inadmissible estimators are undesirable. They should not be considered because inadmissibility guarantees that there is an estimator which dominates the given estimator. So inadmissible estimators should not be considered. Okay, now this is okay. This just follows from the definition why inadmissible estimators should not be considered, because by definition there is an estimator which dominates this inadmissible estimator. So why should I consider an estimator which is inferior at every parametric point theta? But admissibility doesn't mean that it is a good estimator. So let us look at why. So one consider, suppose there is only single observation x which is normal theta 1. I want to estimate theta. L theta A is A minus theta whole square. Now I consider delta Cx to be a constant, an estimator constant. As you vary C, you get a different constant estimator. So these are constant estimators. What I am going to claim is any constant estimator is admissible. And that would suggest that, look, one just by looking at the admissibility, one should not consider that estimator. An example is constant estimators which are admissible, but constant estimator says you don't even consider data. You always estimate, let us say constant estimator 0 says that whatever the data may be, my mean is always 0. So it is a lazy person saying that, look, I don't care about the data, my estimator is always 0. And suddenly you know that mean can be anything in theta belonging to R. So such an estimator would be undesirable because it says you always estimate theta by 0 or in general theta by any constant C. So let's look at delta C is admissible. So any estimator delta C is admissible. So what I do is, suppose delta C naught is inadmissible for some C naught. Inadmissible, what does that mean? That there exists an estimator which dominates this. So this implies that there exists an estimator delta such that expected value of delta x minus theta whole square is less than or equal to expected value of delta C naught minus theta whole square, expected value of delta C naught x minus theta whole square. But delta C naught is always a constant estimator C naught, so this is same as C naught minus theta whole square for every theta belonging to R. And E theta naught delta x minus theta whole square is strictly less than E theta naught of delta C naught x minus theta naught whole square. This should be theta naught because I am talking about risk at the point theta naught, and which is nothing but C naught minus theta naught whole square. What I do over here is, because this is happening for every theta belonging to R, I take theta to be C naught. So this implies that expected value of C naught of delta x minus C naught whole square. So I take theta to, because this holds for every theta, I take theta to be C naught, is always less than or equal to 0. This is what it means. What does that mean? So I write down this in terms of an integral. It is minus infinity to infinity delta C naught, sorry, delta x minus C naught whole square. Because I'm talking about density at the point C naught, so it is 1 by sigma root 2 pi. Sigma is 1, so 1 by root 2 pi e to the power minus 1 by 2 C naught. E to the power minus 2, sigma square is 1, so 2x minus C naught whole square dx is 0. What is this quantity? This whole quantity is always greater than or equal to 0 for every x. So what does that mean? The integral, it's a non-negative quantity whose integral is 0. That means the integrand has to be 0 almost everywhere. So when I say almost everywhere, means the set where it is 0 or the set where it is non-zero cannot contain any open set. So this means delta x minus C naught whole square 1 by root 2 pi e to the power minus 1 by 2 almost everywhere. Almost everywhere means where this is not 0, the set where it is not 0, it cannot contain any interval. So what does that mean? That means delta x equal to C naught almost everywhere. If delta x is C naught almost everywhere, what does that mean? Can you have this inequality over here? Then you cannot have, which implies that expected value at theta naught of delta x minus theta naught whole square is same as expected value of theta naught, because delta x is same as C naught almost everywhere. That means where it is not 0, it does not contain any rectangle. So in integral they will not contribute because they do not contain any interval where it is not 0. So this is same as C naught minus theta naught whole square. In fact, delta x is almost surely almost everywhere is same as C naught. So it is same as C naught minus theta naught whole square. But that is same as, which contradicts, let me call this as 2, because for 2 there should be strict inequality. So you assume that constant estimator is not admissible, and then you got something funny. So what does that mean? Whatever I have assumed, that is not correct. So delta C naught cannot be inadmissible. If it is not inadmissible, it is admissible. So what it suggests is the whole point of this discussion was to emphasize the point just admissibility is not good enough. Any good estimator should be admissible. But an admissible estimator need not always be a good estimator, as we saw that any constant estimator is admissible, but certainly any constant estimator is not a good estimator. Let me now give a situation about the definition of a unique Bayes estimator. A Bayes estimator delta pi with respect to WRT means with respect to prior pi is said to be unique if for any other estimator delta, if its risk is same as risk of delta pi, we have the risk, the frequentist risk of delta and delta pi same almost everywhere with respect to probability distribution of x given theta. So that means r theta delta is same as r theta delta pi. For every theta belonging to theta. So that is the definition of unique base. Let me see if I have written down the exact definition. Definition slightly is different. So what I say is a base estimator delta pi with respect to prior pi is said to be unique if you have any other estimator whose base risk is same as the base risk of the base estimator, which basically means delta is also base. Then we have, then for any other estimator delta with, we have delta is equal to delta pi almost surely. Now when I say almost surely, there has to be a distribution. Distribution has to be in terms of the frequentist distribution, which was conditional distribution of x given theta is equal to theta. Almost surely with respect to distribution of x given theta for every theta. So that means what it means is that is probability that delta x is same as delta pi x. So this is the frequentist probability, which is the probability calculated under f theta, distribution of x given theta. So this is same as 1 for everything. So I say such an estimator is unique base. Now what we'll say that these base estimators have a very nice property. One nice property is that base estimators cannot be outrightly rejected. Generally, base estimators are admissible estimators. So let us try to do that result. So I'll need all the three boards. So let me first erase everything in all the three boards. And then let me do the following theorem, which talks about admissibility of base estimators. So let me write down this theorem. So suppose delta pi is a base estimator with respect to prior. So delta pi is given to be a base estimator with respect to prior pi. First part says if this base estimator is unique base, then it has to be admissible. Unique base in terms of the definition which I gave, that means if there is any other estimator which is base, then r theta delta, the risk of two functions, the frequentist risk of the two functions would always be same for every theta. Second thing is if my theta parametric space is countable, and my prior is such that it gives positive weight to each of these theta. Note that my prior can be such that it gives weight 0 to some of the thetas, right? Because the only condition I need is for pi to be prior distribution, pi should be greater than or equal to 0, and total sum should be 1, because theta is countable over here. I say no, 0 I don't allow, so my prior should be such that pi theta is greater than 0 for every theta belonging to theta. Now, if that is the case, then the Bayes estimator is always admissible. Now, if I have to construct its analog for the continuous case, that means where theta is continuum, or at least it is not countable, then I cannot talk about pi of singletons. There we talk about pi of small intervals, or in other words, pi of any open set. So I say that if my theta is subset of Rk, and pi of B is always positive, so that means my prior pi gives always positive weight to for every open set B in Rk. And if my probability models are such that for every delta so let me just repeat this assumption C. So my assumption C says that the parametric space, which is a subset of whole Rk, is open. So that means it will contain some open set. Pi of B, my prior is such that pi of B is positive for every open set B subset of Rk. And for every delta belonging to class of all decision rules, let me denote that by delta, with R delta theta less than infinity for every theta. So that means for any decision rule whose risk is finite for every theta, R delta theta is a continuous function of theta. So if these conditions are satisfied, what are the conditions? My whole parametric space should be open, and my prior should be such that to any open set it assigns a positive weight, and for any estimator delta, risk function is a continuous function of theta. If that happens, this would imply that delta pi is admissible. So you see, application of all these three results is not that difficult. First is very obvious. If you see that your Bayes action is the unique minimizer, or Bayes estimator is the unique Bayes estimator, you can directly say that it is admissible. Second thing is, if your theta is countable, that means your parametric space is countable, and your prior is such that it gives a positive weight to every point of theta, then also the Bayes estimator would be admissible. Third is slightly more complicated, but it is very much used, especially in the continuous case, that if my parametric space is open, which could be any subset in Rk, and my prior is such that it gives a positive weight to every open set, and my risk function is such that it is always continuous function of theta for any decision rule delta whose risk is finite. If that happens, then also Bayes estimator is also admissible. So Bayes estimator becomes admissible in a lot of situations, what we see. So let's quickly go through the proof, which is not difficult. The A just follows by contradiction. Suppose delta pi is not admissible. If delta pi is not admissible, that means it is inadmissible. So on contrary, suppose delta pi is inadmissible. then by the definition of inadmissibility, what does that mean? There exists an estimator which dominates this estimator. So then there exists an estimator delta star belonging to the class of all estimators such that R delta star theta would always be less than or equal to R delta pi theta for every theta. And there would be strict inequality at some theta naught. But you know one function is smaller than the other variable, other function, so their expected value would also preserve the same inequality. So that means this would imply that integral over theta, so their average with respect to the prior distribution, d pi theta, would always be less than or equal to integral over theta r delta pi theta d pi theta. What is this? This is nothing but the base risk of delta star. And what is this? This is a base risk of a base estimator. So what do you conclude? I conclude that if I assume this, then there is an estimator whose base risk is less than or equal to base risk of r delta pi pi, which means basically the two are same. If the two are same but delta pi is unique, so this would imply r theta delta pi is same as r theta delta star for every theta. In fact, this implies that probability that delta pi x is same as delta star x, that probability is 1 for every theta belonging to theta. That is what the definition of a unique base said. That means if there is any other estimator whose risk is same as r delta pi pi, or whose risk is less than or equal to r delta pi pi, it can never be less than this, right? Because r delta pi is base, so that means this would imply, in fact, this implies that r delta star pi is same as r delta pi pi. Why? Because pi is base. So delta star, the base risk of delta star cannot be less than. But then if this happens and delta pi is unique base, that would imply that delta and delta star, delta pi and delta star are same with probability 1. And the probability calculated with respect to distribution of x given theta. But if delta pi is same as delta star, that means their risk is same, because they are same almost surely. What does that mean? This contradicts one. So I started with something counter hypothesis, and I got something funny. So that means whatever I had assumed in the beginning, that is not correct. So that means delta pi is not inadmissible. If it is not inadmissible, that means delta pi is admissible. Okay, now let's do the part B. So my theta is given to be countable. Countable means it can be, its element can be put in 1-1 correspondence with set of natural numbers, or it is finite. So that means my theta is, suppose theta 1, theta 2. So either theta can be written as this, or it is finite. So that means theta 1, theta 2, theta m. Let us look at. So these are the two scenarios. So again I do by the same way. So on contrary, suppose delta pi is inadmissible. What does that mean? then there exists a delta star such that r theta delta star is less than or equal to so E theta is theta I, so r theta I delta star is less than or equal to r theta I delta for every I for every theta I belonging to theta, and r theta m naught delta star is strictly less than r theta m naught delta for some so what is happening? If I multiply by here theta I, then equality remains because each theta is sorry, I multiply here by pi of theta i's because pi of theta i's are probabilities, so they would be positive, non-negative. So they, in fact, they are strictly positive. By assumption, pi theta is positive. Now note that if I put here pi theta m naught over here, I would get a strict inequality because pi theta m naught was greater than 0. Note that if pi theta m naught was not given to be greater than 0, then this inequality does not imply that pi theta m naught r theta m naught delta star is less than this. Because if theta m naught is 0, then it would become is equal to. So that is why this assumption plays an important role. That means if I apply by pi theta I over here, pi theta m naught over here, the inequalities remain as it is. So this implies that pi theta I of r theta I delta star is always less than or equal to pi of theta I r theta I delta. Note that for this I do not need pi of theta I to be positive. Here even if it is 0, I will have equality, it doesn't matter. It is only the second part I need, that my pi theta m naught should be positive. For to have a strict inequality over here. So because if it was not positive, I would have less than or equal to, not less than, pi theta m naught r theta m naught delta. So I can sum everything. So I sum the inequalities remain, because if you know that ai is less than or equal to bi for every I, then summation ai is less than or equal to summation bi. If ai is less than or equal to bi for every I, but ai naught is less than bi naught for some I naught, then summation ai would be strictly less than summation bi. And that is what I am doing over here. So suppose theta I belongs to theta, pi of theta I r theta I delta star is strictly less than, because at least there is a strict inequality for one element over here. This is same as summation theta I belongs to theta, pi of theta I r theta I. This will be delta pi, because I am assuming delta pi to be inadmissible. Delta pi. But this is nothing but the base risk of delta star, because average of r theta I delta star, theta was countable, is less than r pi delta pi. So that means you have an estimator whose base risk is smaller than the base risk of a base estimator. But that is not possible, because base risk of the base estimator is the smallest possible among all estimators. So this is contradiction. because you know that base risk of a base estimator is always less than or equal to base risk of any other estimator. So you get a contradiction. That means whatever you had assumed in the beginning, that is not correct. So that means delta pi is inadmissible is not correct. That means delta pi is admissible. So what I may do is, let me stop with the proofs of part A and part B today. I can do the proof of the part C tomorrow. So that's all I have for today. So tomorrow when I start, I'll start with the proof of part C. So thank you very much.